What's up, my freshmans and woolmans? This is Harriman coming back at you again with a little bit more balancing chemical equations. Now, this is going to be round two of the balancing chemical equation. Now, last method, the last way I taught, the first video, was on the traditional method of balancing chemical equations. This method that I'm going to be teaching today, I call the poly method, or short for polyatomic ion. Now, the polyatomic ion, or the poly way we balance equations, is when there is a polyatomic ion in a chemical equation. Now, some of you might not know what a polyatomic ion is yet. A polyatomic ion is a covalently bonded molecule. Okay, so electrons are being shared. However, when it reacts with other elements, it actually reacts ionically. If you're more interested in that, you can look up a video. That's another day, another story. So it's a molecule, but it acts ionically when it reacts with other elements. All right, so to do it the poly method, first of all, you got to notice and see the polyatomic ion in a chemical equation. So let's give you a chemical equation illustrated here. Let's do sodium sulfate plus aluminum chloride, and that creates or yields sodium chloride, good old table salt, and aluminum sulfate. All right, now, first things first, the way that I teach this, the way that a lot of new students in balancing notice polyatomic ions, is when a compound in these simple chemical equations have more than two different type of elements. So again, more than two. If we look here, here's sodium, sulfur, and oxygen. So 2 sodium, 1 sulfur, 4 oxygen. Now notice, because there are more than two, there's 3 different elements, not 2 sodiums or 4, but we're saying different elements. An alarm should be going off in our head saying that, hey, we could have a polyatomic ion here. In fact, SO4 is called sulfate. I'll just kind of write this here. You don't need to do this, but this is sulfate. SO4 has 1 sulfur, 4 oxygen covalently bonded together to create a molecule called sulfate, but yet it still is not satisfied and has a 2 minus charge. Again, you are more than welcome to look online to see how that works, but you do not need to know that for this class, okay? All right, now I'm going to link a description down below that will tell you all the polyatomic ions that you should know for this class. All right, so here we go. So when we look at this, we want to do the same counting method we did on the last video, where we write the number of atoms down below. However, there's a trick, and that's what makes it different from the traditional. That is, if you have a polyatomic ion on the reactant side in this case, or the left side of the yield, and the same polyatomic on the right, we want to keep them together. We don't want to separate them. So here, if I'm looking at it, I have SO4. And over here, I have another SO4. Here we have a sulfate, and over here we have some sulfates. Now, because there are sulfates on both sides, it makes it much easier to keep the polyatomic ion together. Don't break it apart. Here's what I mean. If I'm doing the counting like traditional, I have 2 sodiums, but here I don't have 1 sulfur and 4 oxygen. Train your brain a little differently now. Because this is a poly and there's one on the other side of the same nature, another sulfate, this right here is 1 sulfate, just 1 sulfate. Over here on the right, I'm gonna skip just to the right for a second. If I look at SO4 here, I have this time the parentheses and a 3. This tells me I have 3 sulfates. Now, some of you are looking at this and Harriman, you're an idiot. What are you talking about? There's a 4 right there. That's not a 1, but you have to train your brain. There's 1 sulfur and 4 oxygens, but combined, they make 1 sulfate. Now, I explain it like this. Like, think you're making a cake, okay? You're baking a cake. You need like milk or water, 2 cups of sugar, 3 eggs, some baking soda, whatever you need for a cake. But you put all those different amounts, cook it up, and it ends up being 1 cake. So all the little parts become 1 cake. That's kind of like a polyatomic ion when you're balancing. Here we have SO4, we have 4 oxygen and 1 sulfur, but combined makes 1 sulfate. All right, so let's keep numbering. I have 2 sodiums, 1 sulfate, 1 aluminum, 3 chlorines, 1 sodium, 1 chlorine, 2 aluminums, and 3 sulfates. All right, now let's start our balancing. The balancing stays the exact same as the traditional model. We just start with the big uglies, which they kind of all are ugly. So I'm just going to start with the one all the way left. All right, so we have 2 sodiums, 1 sodium. Remember, just recall, the left side must equal the right side to balance the law of conservation of mass. So 2 sodium, 1 sodium. All right, well, they both can go into 2. That's the least common multiple. So I don't have to do anything to this side, so I got to multiply this side by 2. 2 times 1 is 2. And don't forget, what you do to part of it, you got to do the whole thing. 2 times 1 is 2. All right, so let's recount all the way left to right. 2 sodium on the left, 2 on the right, 1 sulfate on the left, 3 sulfates on the right. All right, no big deal. So we got to adjust. Well, what does 1 and 3 both go into? And they both go into 3. So we don't need to do anything to this side, but we need to multiply. Use the coefficient of 3. Remember, you got to multiply the whole thing. Recall, from the traditional method, you cannot change elements. You can't take any away. You can't add them. You can only put a coefficient out in front. A coefficient changes the number of compounds. So 3 times 2 is 6. 3 times 1 is 3. All right, so let's recount. 6 sodium, 2 sodium. Crap, a second ago we balanced them, but now they're not balanced. So we have to go back and fix that. So what does 6 sodium and 2 sodium both go into? Well, they both go into 6. So since they both go into 6, we look at the numbers, 2 and 6. We don't have to mess with this one, but we have to change this too. So now we cross off the coefficient 2, and be careful here, we put a 6. Now, why 6? Why not 3? Why not 3 times 2 is 6? Here's how. You always take the coefficient and multiply it by its original amount. 6 times 1. 6 times 1 is 6. 6 times 1 is 6. Always times by the original. If you do 6 times 2 is 12, or you put a 3 here, 3 times 2 is 12, that's going to be an inaccurate way to do it. Always multiply by the original. All right, so let's double check. 6 sodium, 6 sodium, 3 sulfate, 3 sulfate, 1 aluminum, 2 aluminum. Okay, we got to fix it. 1 and 2, they both can go into 2, so we need a 2 up in front here. We don't need to mess with this one. 2 times 1 is 2. 2 times 3 is 6. All right. Recount. 6 sodium, 6 sodium, 3 sulfate, 3 sulfate, 2 aluminum, 2 aluminum, 6 chlorine, 6 chlorine, and we are done. This is a balanced chemical equation using the polyatomic method. Double check our work for stamp of approval. Make sure all of our coefficients can't be reduced. 3, 2, 6, and 1. They cannot be reduced, so we are good in the hood. This is the correct answer. All right, I'm going to give you a sample problem, and then let's see if you can do it. All right, so let's just kind of move this up a wee bit. All right, let's give you beryllium phosphate plus a little potassium oxide. Oh, that's a bad K. Let's make it a little bit prettier. It yields or creates beryllium oxide and then a little bit of potassium phosphate. All right, so go ahead, pause the video, see if you can do this problem, and then come back and unpause and let's see how well you did. All right, welcome back. Hopefully you paused and did that. Otherwise, I sounded pretty silly if you just kept it playing. But let's go ahead and number them. So first things first, I should have an alarm go off as I look across. Wait a sec. 1, 2, 3. I have 3 different elements. That means I could have a polyatomic ion here. So I look. Hey, I have a PO4 on the left and I have a PO4 on the right. So let's keep them together. Don't break them apart. So watch how we number it. 3 beryllium, 2 phosphates. Again, don't be like, Harriman, 2 times 4 is 8. You need to learn how to multiply. Remember, we're not multiplying. I'm not saying this is 2 phosphorus and 8 oxygen. It's 2 phosphates. Train your brain. 2 potassiums, 1 oxygen, 1 beryllium, 1 oxygen, 3 potassiums, and 1 phosphate. So many mistakes using this method comes right here. They see the 4 and they're like, Harriman, it's 4. It is not 4. That is 1 phosphate. Remember, that's like 4 eggs, cup of milk, whatever else makes 1 cake. This is 1 phosphate. All right, so now that that's done, we start the balancing process. It's all equally ugly, so just wherever we want to start, I'll start on the left, like I usually do if everything's ugly. So 3 beryllium, 1 beryllium. Okay, got to fix it. They both can go into 3. So the only way we can fix that is multiplying or using a coefficient of 3. 3 times 1 is 3. 3 times 1 is 3. Okay, recount. 3 beryllium, 3 beryllium, 2 phosphate, 1 phosphate. All right, well, what does 2 and 1 both go into? That's easy too. We don't have to mess with this side, so we have to put a 2 in front. Remember, this multiplies the whole thing. 2 times 3 is 6. 2 times 1 is 2. Let's recount. 3 beryllium, 3 beryllium, 2 phosphate, 2 phosphate, 2 potassium, 6 potassium. Crap, got to fix it. Well, what can 2 and 3 both go into? Well, they can both go into 6. So I don't have to mess with this one, but I need to put a 3 up here because 3 times 2 is 6, what we're trying to balance. So 3 times 2 is 6. 3 times 1 is 3. 3 beryllium, 3 beryllium, 2 phosphate, 2 phosphate, 6 potassium, 6 potassium, 3 oxygen, 3 oxygen, and we are good in the hood. This, again, is a balancing chemical equation using the Pauli method. And again, the Pauli method is a method used when there are polyatomic ions on both sides of the equation.